started. So that is the future of drone-based deliveries, not these things that hold the package like an egg, but something that is a slung load, and we are the experts on flying at very high speed. So I'm Narayanan Komara. I know you've seen me too much here. I try to stay out of here. And I just want to take you through a bunch of advanced concepts. I accept no blame for Satyanarayana Chakravarti's vast range of things. He has now hijacked everybody to go on a tour of his facilities, so that's going to happen in the afternoon by popular demand. Well, no one is going to threaten to come and visit my lab right now. So, okay. So this is the question. I have a bunch of things that go from dreams to practice, and I want to take you through this joyous world of what I call concept development. Okay, and then what I consider the grand challenges versus the easy problems. So we will talk about things like space-based economy and runway-based space access. And then we'll come down, as Dr. Kalam did, and realize that the real issues are back on Earth. Okay, so we'll talk about hydrogen supersonic transport, which I said I want to see that, because anyway, I don't know if I'll see that or not. But anyway, so we'll go down, and then, so it goes from the blue sky to the green to the brown Earth and realities. At the bottom, I'm saying that we do something other than sit around and dream. We do have some practical projects. So this term tinfoil hat, this Raju has been calling me tinfoil hat forever. This is a bad word used to describe people like me who come up with inexpensive, innovative solutions to problems that others do not yet realize. For example, operating the phone, in a landline phone in our dormitories back in 1970s. People started wondering, eventually the administration started wondering why there was a plastic piece strung by a string from the handle of that telephone. Nobody told them, of course. That was to replace the need to put in any coins to operate it. Okay, that's what innovation, not always. Anyway, so where did this come from? Way back in the 1960s, people who understood electromagnetics and did not sleep through their classes like I did, they said that, look, the government has the ability to intrude into your brain. When you watch TV, they are sending radio waves into your brain to figure out what you're thinking so that they can come and get you. So the way to stop that, they knew, is to wrap your head in aluminum foil while you're watching TV, or tin foil. So that is where that comes about. But today, see, these people, visionaries, because today if you look around, there's a huge business, there has been for quite a long time. All these stealth aircraft and everything is about electromagnetics. Okay, if you look at defense contracting, every component has to be protected against electromagnetic interference. In other words, they're also worried that, so they're all wrapped in tin foil or whatever it is, except very expensive tin foil, billions of dollars. More to the point, nowadays there's a big thing that, people can steal. You see, all credit cards these days have radio frequency identification, whatever codes, and they're saying somebody can walk by you and steal all those codes. So you should wrap your, your wallet in also tin foil. And you don't just do that. You buy something that is 100 or 200, that's much more money than I have in my wallet to pay for the wallet that has RFID protection. So again, millions of dollar business now. So yeah, they laughed at these people, but they were just, these people were just ahead of their times, which is a feature of such people. So now let me take you to, there's a standard operating procedure for developing what I call these far out advanced concepts. I'll tell you that in all seriousness, because through whatever strange mechanisms, I have had the privilege of sitting in the same room as people who were veterans of the Apollo projects. I said, how did these people ever come up with this idea that, in 10 years you can go and land some humans on the moon? I've always wondered about this, and I watched these people very carefully. I realized they have a really systematic procedure of doing this. So somebody tells them, look, you have to do this, somebody's going to step off a spacecraft onto the lunar soil, what's going to happen? Nobody knew in those days. So the way they did that is not sit here and say, oh, how long will it take to get from here to there and there. They just said, look, I'm there. What do I see around me? How did I get here? Okay? And from there they worked out, so they went there and they looked back and said, oh, there is a river there where there is no bridge. If that bridge is built, then I can do the whole of it, all of it. So at least, even if they failed, they came up with the technological limitations, which were subjects of the advanced research. So that is how the research projects were decided. The research projects were not decided by saying, what is somebody publishing in the Journal of Fluid Mechanics or whatever it is, and let's do the same thing. Research projects were decided by saying, take this concept development, and this is the place where if there is a breakthrough, we can solve all these other things. So there is such a process. I'm sure that is done in defense. Every country does some of this, but this is perhaps one of the improvements that people need to realize in formulating their research. The last parts are it's a process of reducing uncertainties. So you do all these things and say, how well do I know this? Oh, it can be either raining or not raining, I don't know. So then you reduce the uncertainty, and eventually you realize that you're pretty sure this is going to happen. So maybe you strap the wings on your back and jump off the cliff. I have done the calculations, I should survive, right? So that is that procedure. So my question here is, how can university is the best position to organize leadership towards such global scale technology projects. And the bad news of this thing for those who want to jump into this is that this is really, really hard science and technology. This is not easy dreaming, saying, oh, I can make energy out of thin air and and immediately go to the newspapers with it. Years and years of hard science and engineering. Okay, so this is really what will integrate all those courses and all the knowledge from there and drive you towards it. Nothing easy about it, which is why I go to the next slide and show you that there is this wonderful process for concept development. You start out with an insoluble grand challenge problems, which is not yet recognized by, I don't want to name any names. The foundations haven't come out and said, put in proposals for this even. You realize that there is such a problem, and you are the person who gets the good idea, and you are honest enough that you want to search for the truth. Okay, that is a very important thing. When you find out things where you don't like the answer, you really should not say that you have an answer. You have to be honest. Then you say, okay, I found out, hey, it looks like it's working, and you tell somebody, and you get these happy reactions. They all laugh at you. Or they say, no, can't be, oh, it won't work. So you find a little piece, way around it, and you get here, and oh, there's an impossible thing, you jump across it. You're very proud. There are people say, no, it'll never work. You climb up, and you reach, I don't know why you want to do that, but you have succeeded. At which point, oh yes, you come and get a ticker tape parade and Padma Bhushan or whatever it is. No, I'm sorry. Everybody says, I knew that. Oh, we already knew that. That's all right. And then you have won. Okay? So you're not going to get rich. Okay? But you can have the satisfaction that you actually you know how to solve a problem. That's all I can promise you that you'll ever get out of that. So the last step is that everybody knows, nobody pays any attention to it, whatever. They've all forgot about it. All right. And then, years later, you know what this picture is? This is people climbing on Mount Everest. When I was growing up, I think a total of 2 people had managed to do that. Sherpa Tenzing, and who I claim dragged his companion Sir Edmund Hillary, who got all the credit for it, up to the peak. But a lot of people have died doing this. But today, apparently, the main risk in climbing Mount Everest is that if you try to come down, you'll get run over by 90-year-old people jogging to the top. I could not believe that. So, all right, so then they say, oh, I've done that too. So I am going to take credit now. Christopher Columbus, actually his name was Cristoforo Colombo, is credited with discovering America. I don't know about that. But he only made 2 trips across the Atlantic, as far as I'm concerned. I have made over 60. So who is better? So I want to give you a test. Here is a request for proposals, or request for quotes. Please read that and see if you can come up with a solution. Does that look complicated? Impossible? No one has done this before? Billions of dollars? That's what it is. It does all those things. Now, if somebody presented this as a concept, everyone would say, I mean, if you have an umbrella, I think I have an umbrella somewhere there. Or do you have an umbrella there? Let me show you how complicated this is. Yeah, right. So see, this, portable, highly packaged, and I think I can, do that. And then I have to do this. And then I have to do that. You try explaining to somebody that this is good, people are going to buy this. And they'll laugh at you. Look at the number of moving parts. Look at the diverse materials that are required. So they'll say, if this was defense contracting, that's $1 million, no doubt about it. Okay? So, but it works. So that is now that you see how advanced concept development works. Okay, somebody had an idea that this would work. And the last part there, you see, it can also be used as a self-defense weapon. Now, what are the grand challenges? To me, the grand challenges are those: hunger, disease, malnutrition, lack of education, dishonesty, injustice, violence, greed, and most of all, people don't read anything that I send them, and then they got all confused. Okay? I can't solve those, but I can solve the easy problems, like global warming, sea level rise, fuel prices, productivity, flood and drought. So let's go on with that. I have actually worked on some of these problems. I have done a lot of hard research work and have 400 and something number of publications done very hard. But in my hometown, couple of years back, I went to the bank and to close an account that had not, And they said, oh, please wait over there. And I went and sat down. Then I saw this young woman go and whisper in the ear of the big boss. And suddenly they said, sir, please come and sit here. I was recognized as the author of, or the person mentioned in the Malayalam Manorama Sunday edition under full page article saying, Malayali builds houses in space. This was a description of a NASA Institute of Advanced Concepts project which I had got. I got phase 1 and phase 2 and we finished both, on how to build large orbital habitats and where you cannot have humans building it because the radiation will kill them. And it has to have artificial gravity, otherwise the people living there will die. So we were, at least the NIAC certified that we had solved that problem. And more to the point, I went and gave a presentation at an agency that cannot be named. And at the end they said, that's boring. We knew you would solve that part. Now let's see the other parts. Anyway, so this whole idea of a space-based economy that Mark Hopkins talked about is pretty radical. It says, look, Earth is just a destination. Imagine that. You live in space, okay? Or you live in a city in space. Earth is an exotic destination. You have to exercise before you go there because otherwise you won't be able to stand up. The gravitational attraction is too much, okay? But it's got nice scenery and whatever it is, so you go there once in a while. All resources and manufacture and customers, everybody is away from Earth. This is a space-based economy. And I think Dr. Kalam dreamt of this. So when we can get out there, it doesn't make any sense to fight wars over who controls a little bit of petroleum resources, because I think the entire moon, Titan, is apparently all petrol stations or whatever it is. I've not been there, but there are resources beyond your imagination, not very far away. What stops us? The biggest problem that people talk about is the vicious circle of launch cost. So the launch cost is so high that it destroys anybody's business plan. Suppose you set up a business plan and say, I'm going to take a loan. When you have to take a loan, somebody has to pay for that launch. You go $4 billion into the red before the thing is launched. And you have to wait 6 years, sometimes it drags on to 10 years, you're paying interest, okay? And if it succeeds, then you have a business, otherwise you're dead. So the insurance is about 1/3 of the launch cost. Okay, because the insurance company will go broke otherwise. And so for them to make money, this is ridiculous. Nobody's going to start a business like this. So this is what stops it. So how can you do that? Well, if there is no business, the market cannot expand. If the market cannot expand, there's no demand. And if there's no demand, then there's no incentive for others to come up and set up new launch services. So until launch services expand, this will continue. So how do you break up? So this is, we are in concept development. We are not paid to sit around and whine. We are paid to win, remember. So we said we need a reliable anchor customer who will put in a demand for enough over a long enough period and is reliable enough to pay that we can go to the bank and say, look, these people are willing to pay for this and they have a pretty good credit rating, so give us a loan to do these kind of things. That person is usually the government or an international organization. No one else can really do that. I don't think commercial entities are going to come out and say, here's $6 billion, I'm going to give this to you at 0.5% interest. Are they crazy? Why would they do that? Okay? So then you need a technological architecture that actually makes sense and is going to do the job, and a policy framework to support these kinds of things, because it's invariably going to be something radically new. So let's look at this. See, both the Ariane 5 launch vehicle and the Airbus A380, which is that humongous thing on the runway, are designed and built by basically the same entities on a grand scale. I think they're both the European consortium of nations, whether they call it EADS or whatever it's space, ESA. They're basically the same bureaucracy, same engineering talent, and same everything. Okay? So why does one cost, look at that, with a 14,000 kilogram payload to transfer orbit, you pay about 165 million to 220 million per launch. Whereas the Airbus, I don't know how much that costs, but I know how much money they make, and therefore their cost must be lower if they're profitable, right? This is the way we figure out all these things. We are dealing with a situation with huge unknowns. Nobody's going to give us data. So we had to do our own intelligence and figure out. So I can be sure that they must be, if they are not going out of business, then their cost is no more than 1.22 million per flight, which is launch and landing. Why is this so much different? I mean, look at the gross weight is about, it's not that different. So the answer is that this vertical launch requires what is called a standing army of people. Okay, somebody tried to figure out the cost of a space shuttle launch long time back. And the problem is, how many launches are you going to make in a year? When the space shuttle was originally proposed to Congress, it was to build space solar power, which was the anchor customer that they argued about. The original paper on this came from Peter Glaser, who was not an engineering company person, remember. He was a vice president of Arthur Andersen consulting firm. Okay, so he came out of this paper saying, oh, space solar power, and everybody still talks about that paper. But fundamentally, they said we will have 5 launches a week. I think there was something like that, space shuttle. 5 launches a week. Then the cost would be something very low. The reality was maybe 1 launch a year or 2 launches a year. So then the trouble is that you can't just fire everybody and say, oh, we'll call you when we need you and come in here. You got to have. So that is the reason, single reason why space launch costs so much. Okay, you need these huge towers. Professor Chakravarti was talking about fragmenting those into tiny things, but that's not possible for some things. So if we could, so the Airbus on the other hand is a runway-based system. Okay, so can we do runway-based space launch? The trouble is, yes, people have been talking about this. And you go there and say, oh, we ran this huge multidisciplinary optimization code which went through this, and we looked at a global optima, and nobody has a clue what is inside that code. Okay? And what they do in those codes is adopt the path of minimum risk. What is the path of minimum risk? Do what has been done before. So the moment you come out with a new concept, your risk is red flag and you're dead. So we said, no, I want to develop, not back of the envelope really, but Microsoft Excel level calculation based on undergraduate level science and technology to do this. And we have done that. We know that this can be done with 2-stage to orbit. We can decide, 3-stage to orbit, 2-stage to orbit. We chose 2-stage to orbit, and I think that's the right choice. Where the lower stage is simply an A380 class vehicle. It's not an A380, you don't need seats in there, you don't need whatever in there. A380 class vehicle, so it can land and take off on those same runways. Okay? It picks up oxygen on the way up. So there's no reason to carry the oxygen. Oxygen is, you know, the thing about rocket fuel is a rocket fuel ideal, best chemical rocket fuel is hydrogen oxygen. Okay? Hydrogen oxygen is H2 plus O, right? H2 is, you convert these things to mass. H2 is like 2 and O is 16. So 16 out of 18 of that rocket fuel is oxygen, not hydrogen. Why do you want to carry the oxygen up? So people have been trying to do this whole idea of liquid air cycle engine where you pick up the oxygen on the way up. Trouble is everybody says, oh, that costs too much. Oh, we don't have a fleet size that can justify it. So even DARPA, all these people joined together and they said the best alternative is to put a rocket on top of a 747 and fly. I asked the people, I said, come on, you know, that's so depressing. Why did you do it? And that's what they said. We don't have a market for it. So we had to find a market for this to make it work. That is all that is needed. So we said, space solar power. Back to space solar power. Anchor. This is why Dr. Abdul Kalam was so keen on this. It's not going to happen tomorrow, I can tell you that. But it will happen sometime. The thing to remember about space solar power is why. Which, you know, you can't get us space freaks to think about that because we want to see the thing fly first. Okay, there's all these other things. But the reality is that nobody wants space solar power just to admire one thing there. Okay, it only makes sense if it can replace, you know, the promise is infinite power. Oh my goodness, you know, power is too cheap to meter. There's, etc., etc. This grand dream, everybody is going to be so rich. That can only happen if we are able to replace all of fossil power. Okay, so what is that? 4 terawatts at least, assuming we cut down from 8 terawatts to 4 terawatts. That's 4,000 gigawatts. You know, a typical nuclear reactor is, it used to be like 200 megawatt, then it went to 400 megawatt, then it went to 700 megawatt. Now I would say there is about 1 gigawatt, maybe 1.2. And somebody from the Indian, atomic energy people actually explained that to me, or not to me, but I was in the audience. They said it's not that we didn't know how to build a 700 or 1.2 gigawatt reactor. What would you do with the power? We don't have the power grid, right? So when the power grid has to come up in order to do this. So I can use the same reasoning. Now I'm very far away from aerospace engineering. I don't know anything about nuclear power. I don't know anything about power, come to think of it. I just know that electricity there are two kinds of electricity, the red and the green. The green goes through the green wire and the red goes through the red wire, and that's okay. So 1 gigawatt is a good unit for a power station, whether it is nuclear or space solar or anything, if you're going to put the power into the grid. So we are talking about 4,000 1 gigawatt stations flying around. This is space solar power. So this is the point, we reach there. What does it look like? It looks like 4,000 stations. It's not like one station. Okay? One station is not a good idea because one stone comes and hits it flying at 20,000 miles an hour. That's the end of everything. So anyway, there is a metric for space solar power called specific power. That is the power that you can get delivered. I would define it like that. Nothing else makes any sense. It's not enough to manufacture it if you can't deliver it. Power delivered into the ground per kilogram that you have to put in orbit. Okay, so this defines the space part of it. So I choose the value 1, and we have done enough calculation. So a specific power of 1 kilowatt per kilogram. If we do that, then we can calculate how much mass is needed for this system. So you see, now you started with knowing nothing, and I still know nothing, but I now have a system design. 4,000 1 gigawatt stations, and I know how much it weighs. I can translate that to number of launches needed for payload capacity. This is how this process goes about. So we designed it on, why 25,000 kilogram payload? That's a space shuttle payload. So it's been done before. People know how to deal with that. So as far as possible, you hold on to things that others have done and make sure they're not slippery and all these things, and you climb up a little bit. And this is the process. Okay? What is the roadblock? So when we went this way, one thing I will say that I hope Mark Hopkins forgives me for this. I do not believe that when you go to this level, when you go to 1 gigawatt level, you will not use photovoltaic power. Because there is no scaling advantage with photovoltaic. If it takes 1 square meter to capture 1 kilowatt of heat, it takes 10 square meters to capture 10 kilowatts. And it takes 100 to capture 100 and million to capture million. Jet engines don't work that way. You can ask professors. I think I know he knows enough to tell you that. A jet engine that weighs a factor of 2 more can probably generate 5 times the power. Jet engine that weighs 10 times more can probably generate 100 times more power. So the mass goes up very slowly as the power increases. So if you want to generate 1 gigawatt, which one would you use? You would naturally go with our design is it's a long way back. I think it was 125 megawatt gas turbines, 8 of them, so that if one conks out, you're still in business. And that is our basic design. Now those can be carried on reasonably small vehicles. So that is our design. Then how do you transfer the power? So there are several things there. I don't take too much time to do that. But when all is said and done, we said we can do this. We can achieve better than 1 kilowatt per kilogram. Actually, we think we can do 1.6 kilowatt per kilogram. Although that may be a little bit too optimistic. If all of it is not lost in transmission. Okay? But the transmission cannot be done at the low frequencies that people are talking about. It's just not practical in my opinion. And that's not just opinion, that is, I think, physics. No, I haven't seen anything to counter that. That's where I said it's hard science. It comes out of very fundamental theory called diffraction, which also I slept through. They did try to teach me that in the physics lecture theater, which is close by. I slept through that to my regret, but I think that no one has found a way around it. Diffraction limited loss dictates that you must bring down the distance and you must increase the frequency to reduce the size of the infrastructure. Okay? And so to do that, instead of 2.4 gigahertz, which is chosen because you don't want to get close to the 10 gigahertz vibration frequency of water vapor, we should go to 200 gigahertz where there is actually a nice transmission window. The trouble with 200 gigahertz, I don't know if I went through that or not. There you go. The trouble with 200 gigahertz is that it gets absorbed very nicely by the lower atmosphere. Not just water vapor, but oxygen, nitrogen, whatever it is. So that was a huge problem until I had dinner with Professor Rajkumar Pant of IIT Bombay once, and he's an expert on lighter than air aerostats. And I eventually asked him, so they tie it up, and I said, hey, how big are these? And they are usually parked at 12,000 feet, 4,000 meters to be above the monsoon clouds. And I said, how thick is the cable? And he said, 50 millimeter, Kevlar wound, right. So I said, why? Oh, we had to put, the hydrogen compensation and electric wires and communication, all these things. And that's enough to put a waveguide that operates at 200 gigahertz with very, very, very high efficiency. You can evacuate the waveguide. It essentially comes down to space transmission. So we can solve that lower atmosphere transit. So we can solve all the problems. This is the thing about the distance. See, that is geosynchronous Earth orbit. You're up there and Earth looks like that. This is a 2,000 kilometer orbit, which we choose. The downside is that you have to keep going. Also, people said, oh, you need a constellation of 10 or more. Oh, that's so bad. That's what I said. Remember, the real system will have 4,000. Okay? 6 or 10 is not really of interest to anybody. So it's there. All right, so this is our design. We pushed this as far as we could through papers presented up to 2013, but we hit this roadblock. I think this is a better roadblock to hit than launch cost and things like that, because I happen to know that in the automobile industry, they use 77 gigahertz for radar, collision prevention radar, and maybe now for these self-piloted cars. And the way they get 77 gigahertz, I know from an insider in the industry, my big sister, that they actually generate 220 gigahertz and then use some division or multiplication to get the 77. So there is research on 220 gigahertz. There's commercial interest in advancing the efficiency of that. From looking at military systems, no one's going to tell me anything about military systems, but I worked out some calculations and said, these people have a lot better efficiency. Okay, otherwise they can't. They use 220 gigahertz for pilot goggles in helicopters to fly through dust clouds. You can't put something, 1-ton converter is not going to fit in a helicopter. So they've figured out how to do this. They're not going to tell us, but sooner or later, 10 years down the line, it'll be commercial. So I think this is a better bet. But for now, I had to stop. Okay, there's no point in pushing ahead. And this is what happens if you're, that's what I said, that's the honesty part. There's no point in my claiming that I can do space solar power until this happens. President Kalam realized that the grand challenges are much closer to home. But the procedure is the same and it needs the same approach. That's what he was saying. We need to bring the same space concept. Rocket science has to be brought to these problems. One is supersonic hydrogen transportation. Everybody says, oh, it doesn't work. Oh my goodness, the power goes as cube of speed, and if you double the speed, the power goes up by 8 times, or the weight keep. I know, I've heard all these things. I agree. I can do the calculation enough to agree that a hydrocarbon-powered supersonic transport is not a viable idea. Sorry. Okay. They can go, business jets where people don't care about money. They can do that. Fighter planes, they can do that. I am not going to be able to afford the ticket on one of those, and then I have no interest in it. But if you go to hydrogen, the situation is very, very different, because hydrogen delivers essentially 4 times as much power, as much energy per unit mass as hydrocarbon fuel. And that has a huge nonlinear effect. For the same payload, the whole aircraft is much smaller. I mean, hopefully not smaller, don't make the seats any smaller, but much lighter, okay? And so this actually works. We've done the calculations, and it's like, but the hydrogen is too light and you need a big tank. Yes, so the drag coefficient goes up. But the thing is smaller, so the actual drag is half. We have managed, as far as I know, we can do one trip, 10,000 mile range, which is essentially the trips that Professor Chakravarti goes on every week, we can do now with the supersonic transport, no problem. Okay, so that will work. Why? Why doesn't NASA do this? This is what, whenever I suggest anything like this in Indian universities, somebody asks, is NASA doing this? No, because NASA is interested only in crossing the Atlantic and Pacific Oceans. Okay, they have no interest in crossing the Indian Ocean. And the last study that was done, I've actually seen the results from that. They took a study done in the Cold War days, and they said there's no other market, and they showed the Western Hemisphere. The entire Eastern Hemisphere was missing. What has changed since 1990? The demographics have changed very dramatically. Look at all these stars. They're not Communist Party symbols. These are all destinations that became viable after 1990. Because, in 1990, you could not travel to South Africa. Your passport, if you use an Indian passport, it said not valid for travel to South Africa and Rhodesia. If you go there, you won't come back. Okay, not anymore. South Africa is a very viable destination. China is a very viable destination, and there are a lot of GMs, grandmothers in China and India, who want to travel long distances. So it's not all James Bond and drug dealers swinging briefcases going on these trips, as NASA's projections seem to show. It's not all business class passengers. Okay, so anyway, this is why it needs a new look, and this is why India is the best location. And it's not just India. I happen to know what is the real center for it. It is Nedumbasheri International Airport near Cochin, which just happens by pure coincidence to be 1 hour from my ancestral place in Thrissur. Okay, so all right. Okay, so now that I have brainwashed you into thinking in these terms, let's look at global warming. So everybody says, oh my goodness, we're all going to die. What is the problem? Well, the Earth is heating up. The latest data, and I'm not going to question the data because they've done their science. 2.92 watts per square meter is the heating rate. All the time it's capturing that much heat and retaining it. The incoming heat is more than the outgoing heat. Terrible. And greenhouse gases are blamed for a lot of that. So what are the solutions? Well, you reduce the heat. Don't put in so much heat into the atmosphere. Or I'll reduce the emissions so that these things won't pick up so much heat and retain it. So that is where all the focus is, reduce greenhouse gas emissions. The best way actually is simply plant trees, because trees capture carbon. I mean, what are the trees made of? It's carbon and hydrogen, as far as I can tell. Hydrogen is very little of the mass. So most of the mass is real carbon. You're capturing carbon, which won't become carbon dioxide unless you burn it. But if you really want to make an impact and you want to reverse the climate back to 1990, which is the target, or 1872, which is the start of the industrial era apparently, you need to increase forest cover by 1.5 times. 1.5 times. Sounds quite small. Plant another Amazon forest. Okay. Or do it all over the world, one tree at a time. But it will take a lot of time. And maybe we don't have that much time. So what else can you do? Well, unfortunately, the global agencies tend to adopt this approach. If you read what I read in the West, you would all get very angry, because they all say that the problem is all these people in India and China who are burning coal and burning wood and heating up the world. And if you look at per capita emissions, it is like, an American emits 20 times or 50 times as much as the average Indian. But they don't know that, or they refuse to believe that. So the agencies come and say, you can't do wood burning. Okay, you have to use natural gas. Why natural gas? Because methane. Natural gas is mostly methane. Methane is 20 times as bad as CO2 if it is allowed to go into the atmosphere. And they are putting a lot of methane into the atmosphere by fracking to extract petroleum. They need to get rid of it, and so that sending it to Indian kitchens is a good way to get rid of it and convert it to carbon dioxide. It's good. I know it has all these things, but I don't see that as a good solution. If you read presentations from Africa on this whole idea of climate change and all these things, they are very angry, because these agencies are telling them basically, oh, we don't care if you starve. Okay, the problem is all you people cooking for your children. So anyway, I don't think those are. So we come to the only other why don't we reflect the heat before it ever gets absorbed? Okay, is this really impossible? So that is the aluminum foil hat idea. And is NASA doing this? I have to tell you, NASA is not doing this. And we came very close. Last year, we put in these pre-step A, NASA Institute of Advanced Concepts, pre-proposals, and it got accepted. Said, oh no, now they want us to write the full proposal so that they can laugh at us. So we wrote the full proposals and got it in. It got extremely good reviews, which does not happen to me a lot. When I put in papers, they say, kill the paper, kill the author if possible, whatever it is. And then I fight and claw, and eventually it gets accepted. No, this is the number one problem facing humanity. What they have suggested is a viable approach. It's a step-by-step thing. It's not going to be something destroy anything. It can be flight tested and all these things. So it got extremely good ratings. The integrative panel said, not only did they say we don't have money to do this, they put a red flag on it saying don't fund this. Because they said there may be other climatological impact. That's the whole point of getting a funded study, so we can study these things. But you have to look at it from their point of view. What would have happened if they had funded it? Next day's newspaper would have said, NASA funds project to end global warming. Can you imagine the political firestorm that comes out of that? So I said, look, those poor guys or poor girls, they value their jobs too much. So that, I think, is the reason why NASA is not funding it. We did come very close. But as far as I'm concerned, the concept is sound. We are moving ahead with calculations and things like that, and we have our own guerrilla networks to push these kind of things. We have model scale flight tests done by freshmen and sophomores that are working, and we are slowly going to push it. India is the ideal place to test this, by the way, because you have a clear ocean all the way down to Antarctica. We could test that, and nobody's bothered with it. So I hope somebody in India picks up on this thing and helps us with it. We can save the world. So as far as I am concerned as a concept developer, global warming can be not only reduced, not only stopped, but reversed all the way to 1990 or 1872 if humanity wants to do it. And the cost is not that great. Okay? A few $100 billion. It's not cheap. A few $100 billion. Would you pay that to kill global warming completely? Yes. So, all right. So now we get to the real problem. This is our roadmap for revolutionizing India and Indian villages. We start by the first photovoltaic systems given to schools. Because if nothing else works, those children are going to learn. And in 5 years, 10 years, They will look at solar power or, the photovoltaic systems and solar panels and silicon chips. There'll be enough broken silicon chips flying around. If they play cricket near this thing or try to down mangoes from a tree, there are going to be a lot of broken solar panels. So they'll have held all these things in their hands. They'll have read the manuals. They will have helped their teachers troubleshoot these things. They will be comfortable with the technology. I will have one. Okay? Nothing else happens. But we think a lot more will happen. We hope to see pictures of things like this. That is a power drill. Okay? I'll tell you why I'm so enthusiastic about it. The deck outside our home decayed and was falling down, so I eventually said, take it out. And there was no deck there. Then I said, okay, I better put up a set of steps so that we don't fall out of the kitchen on 4 feet down. I built those things in 2 of these things in 1 afternoon each. And you can ask her my usual schedule for doing anything. I start a project and then 6 months later, things are dragging out. This is because that power screwdriver plus drill is so convenient. Even somebody as incompetent as I can drive in 100 or 200 screws in an hour. Try doing that with your hand through real wood. I don't see these in India. I don't think anybody, I'm sure it's available in India. I've looked on Amazon. I don't see anybody saying, if I have power in my village, I will get power tools. This idea is not there. So we want to bring that around. Then we want to bring in biogas, which will produce 4 times as much energy per unit cost as photovoltaic. So that's the real way to scale up. We want to bring in university test beds. Then we want to go to all these high-tech manufacturing. Make those gas turbine blades for Professor Chakravarti's millions of gas turbines. Ideally suited. 3D printing with metal boards these days. Can be done in villages. There's no reason why you can't do it. Can you do, what about quality control? Suppose you need 200 blades. Will it work if 10 blades are made here and 10 blades are made there and 10 blades are made? I think so, because the contract will come through the internet. Exactly the same specifications will go to each person. Exactly the same machines are doing these things. It's no different. Quality control is no different than if it was done on a big factory floor. Okay? So contracting can be done through the internet. I don't like the idea of blockchain, but fundamentally they say that it enables secure transactions and all these things. So conceivably you could take a tender from whoever, gas turbine research establishment in Bangalore or wherever it is, and be sitting in a village somewhere in Bihar and get that order and put in your own proposal, win the contract, and 1,000 others can do the same thing. You promise some delivery dates. You go and make these things and send your 10 blades and everything gets assembled. Why not? So I'm too stupid to imagine many other alternative professions, but we've heard many ideas. So use that to get more power, then go to intensified solar, which is just focusing sunlight. It only works when the sun is shining, I know. But you can do all this, he showed where high pressure and room temperature can be used to generate liquid fuel. Research that I have seen uses high temperature and probably just ordinary pressure, no air, to generate syngas and liquid fuel, okay, in the villages. And they were complaining, saying, we know this works at lab scale, and they showed this 55-gallon drum. But we don't know how it will work when we produce at a scale enough to compete with the US oil industry. And I said, wrong problem. That 55-gallon drum is energy independence for an Indian village. Okay, so why don't you bring that out here? Well, it hasn't happened yet. We hope that happens, but it's possible. Then you bring in wind turbines. I hate to say this again, but wind turbines are not going to be the solution. I thought they would be when I started out. I'm the expert on aerodynamics and whatever it is, and we've built many wind turbines. Sorry, that'll be it's too complicated. So with this, we think, and bring in corporate social responsibility, public-private, all these kind of things, we can get to megawatts in each village if we want it. I don't think we'll need it. 100 kilowatt per village is probably more than you can use. We'll have energy independence. No more $125 billion fuel import bill. What will that do to the rupee value? What will it do to the economy? So that's our plan. Reforestation, I think it can be done, and people are actually doing it. I think they need all our support. So, but it takes a long time. You better start now instead of sitting around talking about planting 10,000 trees 5 years from now. Start today. Okay, it takes a while. So I think we can reverse it. There are a lot of technologies which I don't know about, but I have, in those working group reports we have on, people are developing techniques, bacteria, whatever it is, to eat all these pollution. So all these things, there is technology. Reduce the footprint required for agriculture and actually reduce the weather impact on farming, so that say, oh my goodness, monsoon is late by 1 week, I'm going to commit suicide. Not necessary. Okay, you can actually make it independent of that quite a lot. Not entirely. I mean, it's not something to kid about, I know, but the problem is really, really so bad. But why should we be so dependent on precise timing of the monsoon? Okay, there are techniques, but you need energy. And what's the relation to space? Believe it or not, there are enough tinfoil hat people out there who have ideas for converting Mars to a resort where you can jump around because gravity is only 1/3. Okay, you just put a big bulb over it and put in whatever. So terraforming technologies are there. There are proposals to turn the Sahara into a green, nice place, and turn the Thar desert into cultivation and all these things. So why not do that? Vertical farming is very much is viable. It is energy intensive. It's very technology intensive. I've seen research where they said, oh, we think we should control the temperature. Eventually they figured out what they needed to control was humidity. Okay, I've seen the startup company presentations, whatever. So it is technologically intensive, but come on, the technology needed is our technology for our plants. It's not imported technology on how to grow pine trees. You don't care, right? Here's a takeaway. Today if you want to get carbon credits, how do you do this? Oh yes, there are consultants who will come in, and from the IPCC or whatever in Geneva, all these people in suits and ties will come in, fly in on jet airliners, and you will end up paying $100,000, not rupees, to get the certification needed so that you can get 10 cents back on every ton of carbon dioxide that you save, or $2 back or whatever. It cannot be done at a small level. It can only be done by very big entities like the government or big industry. Why? Why not make this possible to do for every Indian at least, with some, there needs to be measurement and certification technologies and all these kind of things. I mean, how tough is that with technology? So if you allow people to actually get carbon credits, and it should not be, why only carbon credits? Why don't you get credit for cleaning up your river? Why don't you get credit for picking up the garbage? Okay, it needs controls, but this in one step, I feel, will allow 1 billion people to participate in this instead of sitting there saying, what is the government doing? Okay, and I feel that if nothing else, and tell people to carry reflective umbrellas, not when it's raining, but they'll be sending energy back into space. And so now let's see. I don't know, I don't think, anyway, you saw that thing flying. So people, I think the classic statement from Sri Lalu Prasad Yadav was, Bijli nahi, sadak nahi, computer ka kya fayda? Very good point. But I think we can bring the bijli. We already saw that, the electricity. Okay, the translation is no electricity, no roads. What's the point of having computers in villages? So we can bring the electricity, and with that, electronic commerce and the sadak, the roads, we can't do anything about in the short term, but I think the drones are the solution. Blame him if they don't come out. Okay? So I think we can solve these problems. We can make villages really viable places. There are concerns, there's all kinds of things, but I think those can be dealt with. Here's a very interesting thing that I haven't seen anywhere else. Fundamentally the average Indian worker is a lot smaller than the average European or American worker, maybe even African workers. So isn't productivity going to be a function of this? Can you work as hard and lift when in our home, I've seen, I take great pains to push this thing a little bit, and the guy comes in and picks it up. First time I was going to America, I had this one suitcase, inside which there were long playing records or whatever I had. And at Frankfurt airport, they had just had a terrorist attack where somebody got on a Lufthansa plane and shot the pilot and all these things. So this is very long before 9/11 and all these kind of things, remember. So they put in their own security system. They made everybody identify their bags, and only then it was loaded onto the truck to put in. And when you actually walked inside the plane, they searched your hand baggage. Okay. So he had to go there and say, that's my bag. And there were these two guys standing there. And this is my bag that I pick it up. That's how the truck was loaded. I said, all my records are gone. Nothing broke actually. That's my packing, of course. Spacecraft quality packaging. But isn't this a fundamental disadvantage? Apparently not. Look at that tech concept there. Look at this, the gentleman from Korea. Korean workers are not as big as European workers. They built an exoskeleton and they are basically controlling the actuators inside that. Okay? So you can work, in 8 hours you can do the work that would take 20 hours to do otherwise, because this has got power. Of course you need energy for it. I think this concept will be wonderful. You can do a lot of things in Indian villages, of course. It might displace a lot of people's jobs, but I think you should consider whether those jobs shouldn't be replaced in the first place and get people working on something better. So that's a very interesting concept. Of course it is military applications, which is where it was funded. Yeah, we can do a lot by technology in e-governance, which is already being done. The justice system, I hope, can benefit from this a great deal. And so you can, I don't want to get too much into that, because I read every day about people who say unwise things about the Supreme Court or something and end up in jail. I'm sorry. The final problem is top quality medical care accessible anywhere. Without that, people are not going to agree to go from the cities and live in the villages. Can this be done? I think absolutely. Is there a really Indian approach to doing this so that the costs don't balloon out of control? In the United States, my insurance premium, I'm getting older and creakier. Parts are all beyond warranty. Most of my bodies are beyond the design life. But still, the insurance premium shoots up for absolutely no reason, 10 times the rate of inflation. Why? I don't know. But I think it can be done a lot better. And we'll hear more about that tomorrow, so I don't want to get into that. Okay? But I think there are innovative things that can be done. So take away ideas. I want to tell you. So we say, why don't you go ahead and do this and start up a company? I'm sorry, I am not smart enough to be a billionaire. Actually, you think about that. What do you see the billionaires doing once they make the billions? I don't want to name any names, but they try to become concept developers. They try to set up space launch companies and this and that. So in their hearts, they want to become what I already am. Okay. The other side of it is, I've thought about it. What would I do if I had $1 billion? My life would be ruined. Because after that, I can say anything outrageous here and nobody cares. But imagine if I was a billionaire and I stood here and said these things. Next day, I would be in big trouble on Facebook and Twitter and everywhere. So my whole freedom is taken away and everything is. But this is the really radical thought that made me so happy. That I see all these billionaires, after struggling so hard and making their billions, try to do what I am already doing. Very happy. Okay? So we are not concept developers. Don't ask concept developers to go out and implement these things and scale up. That is really somebody else's job. We are not cut out for that. Okay? And you really need to look at that statistic. That comes from the US National Science Foundation. 93+% of American venture capitalists funded. So the venture capitalists did their due diligence and funded these companies. 93% of them, according to the National Science Foundation, go broke in the first 2 years. So it's not something to go, oh, my child, I want you to become a venture capital startup entrepreneur. That is like becoming a basketball superstar or a cricket test player. The chances are much about that. So this is the takeaway ideas. Look, instead of these Darwinian systems, which is like, survival of the fittest, which is what the venture capital whole idea is. 99% died, but you won, so we all talk about you. That's really very wasteful. You lost 99% of the good ideas and hard work in that process. Why is that the best way to do things? It's not going to work where the end use customer doesn't have much money. Think about that. Okay? So anyway, that's what we want to do. I think this is ideal for undergraduate participation. And so let me stop with that and go eat lunch. Thank you very much.
Just before lunch, I'll take a minute. Questions? Go ahead.
First of all, thanks a lot for hosting the Talk. microwave transmission, modulated and demodulated at Earth. Am I correct? That's one question. Number two, I might as well finish the other one. You talked about Dr. Kalam imagining space habitats with Earth as only resort. Is that really viable without culturally bereft space sustaining human life? That is a philosophical question. The first question I asked was about the space power energy transmission. I thought that had been solved.
On both of these things, let me first say that you saw the diagram of the concept developer. You work hard and come out with a concept, and all the rest of us sit around and say, not going to work. So I am now the not going to work person on that. Okay, I am that grinning face. The difficulty with transmission is something that is, I didn't study this, I slept through the classes. But diffraction is what kills it. There is a diffraction limited beam size that can be generated from something of finite aperture. Let me tell you one thing. The sun looks like a point source to us. It's not a point source. If you take sunlight, it looks like it's going very straight, right? But over a distance of 100 kilometers or 1,000 kilometers, sunlight diverges at like 0.5 degrees. Even sunlight, because the sun is really not a point. It's actually a disk, very big disk, even seen from here. So likewise, the divergence of the beam depends on the size of the transmitter, and the size of the receiver required to capture it, and the distance between them, and the frequency at which this transmission is done. Okay. Fundamentally, the larger the distance, the bigger the beam is. The lower the frequency, the bigger the beam. So there is a huge difference between 2 gigahertz and 200 gigahertz. At 2 gigahertz, I'm sorry, those numbers are not nice. Okay. Have you seen any actual demonstration of a significant amount of power delivered and captured with even the theoretical efficiency? No. You lose a lot. A lot of it spills out. So that's the other thing. People are typically happy in communications if an antenna captures the inner lobe. This beam, because it comes out of it, actually because of interference and all these, it's rings. There's a central disk if you do it right, and then there are rings. So communication people are not worried about it. If they capture the ring, central ring, they're pretty happy about it. The rest can go away. But you can't transmit power like that. Your power station will be the central ring, and your neighbors are going to get fried 10 miles away. I don't think they're going to like it. And you don't want to be a power company that wastes 16% all the time. So if you take all these things around, there is no good solution. Okay, you have to go to high frequency. As far as but I'm perhaps in a minority of maybe not one. I think Dr. Kalam in his eventual days he did come around to the idea. I started seeing the term millimeter wave in those presentations towards the end, and I take the blame or credit for that. So no, it's not a solved problem. It can be done. Railways uses 7 gigahertz.
Pardon?
Indian Railways uses 7 gigahertz transmission. They've been doing it for a very long time, but it's tower to tower, short distance. If they put copper line, somebody will run away with the copper line, or it's too expensive. But no, not over a very large distance. Sorry. What is the second one? This whole idea of. So different people have been talking about it. In the 1970s, at least when I was growing up, the Malthusian theory was attained, right? They said by 1990, population explosion, people will be all eating each other and all these things. Oh, we need better places to go. So that was part of the motivation. Okay.
Mr. Fuller.
Yeah, right. Or they say, suppose, one of these days we're going to see that a little object there, and when we look at it, it looks blue. Because it's blue shifted radiation, which means it's heading for us. And it's not moving, which means it's heading straight for us. What do we do? You see? So we decide, what is that? They said, what will you do if you realize that you only 5 years to live before that hits us? They said, you pick up the 100 smartest people in the world and put them on a rocket and launch them towards that, and then it becomes their problem, something like that. So these were the circumstances. Or one day you realize that the sun is actually becoming a red giant. So, but otherwise, yeah, you had a question.
Culturally bereft space habitats,
yeah,
I don't
yeah,
know.
right.
What is culture? Human beings.
Yeah, but the human
Humans will
beings
create their
deeply
culture.
bereft of the earth.
Well, but I'll tell you the other side of it. 3 generations down, child born on that, why would they have any contact with Earth? To them, Earth is just blue something in the sky. They will have no recollection of it. They will form their own, somebody who has been transplanted for so many years.
I can't pick up life in those
Yeah,
mosquitoes.
right. So, your grandmothers used to tell stories about this place. Do you have no other connection? Right. I hope, yeah.
Can you allude to passive solar as a means to eliminate the...
So passive solar is very good, but it does have its downsides. What are you going to do? The process of making solar cells involves sulfuric acid. Okay, so the process is pretty ugly, and the disposal of these things is pretty ugly. So yeah.
But passive solar is not just composition. Passive solar is all about a mix of architecture.
Oh yeah, right. So these, yeah, right. So these things should be done. They are all no-brainers. People should be doing this all the time.
Using
Right.
plastic bottles.
Absolutely.
Water.
Absolutely. Yeah. What works? That's wonderful. Yeah. I think let's stop there.
Okay, thanks a lot, Professor Kumrit. We will take a shorter lunch break. I request all of you to come back by 12:50. So the afternoon schedule, I'll just read it out. From 12:50 to 1:50 will be Working Group 2, Renewing Mother Earth. 1:50 to 2:20 will have Space Technology for the Nation. 2:20 to 2:50 will be Village Development Experience. 2:50 to 3:20 will be Flood Control. 3:20 to 4:15 will be Hydrogen Village and Thorium Cycle Concept. 4:15 to 4:25 will take a shorter tea break. 4:25 to 5:15 will have panel discussion, Reaching New Resources. 5:15 to 6 p.m. will be NCCRD and Research Park lab tours. Thank you. We'll all assemble back at 12:50, please. Thank you.
Good afternoon to one and all. I hope they must reduce the gain, I hope. Sounds too loud, right? No, it's okay? Okay, thank you. Basically, I have spent about 36 years as part and parcel of the Indian space program, particularly connected with the launch vehicles or rockets as commonly referred to. Dr. Kalam has been my senior. I joined in 1970, whereas he became a part of the Indian space program starting from 1962 or so. He was one of the first 4 recruits taken in as part of the space program to start the activities on the launch vehicles. Over the years, the space program has matured a lot, and we are right in forefront of or comparable with any other country that is in this field. Certainly, we don't spend so much of money as particularly the US, so therefore our programs are much smaller in size than what you will see like a space shuttle and all. But then the space is a very costly affair, and certainly yes, there have been always questions why India is spending money in the space. I think this has been answered right at the beginning of initiation of the space program by the father of the space program, Dr. Vikram Sarabhai. His statement is very clear, telling that, look, we don't have fantasy ideas about space, but we should be second to none in the application of space technology towards the real problems of mankind, particularly here with reference to the Indian population. Okay, starting with this very aim, the space segment basically has got 3 kind of zones of functionally, if one may say. There is, of course, the space applications, what we see right on the ground. It may be communication, it can be telephony, it can be the TV broadcasting, it can be remote sensing, it can be teleeducation, it can be telemedicine. This is the part which directly interfaces with the common man and then benefits him a lot. In support of this, we need to have certain space assets in the space in the form of spacecraft. That is the space segment of the space program. And then you need to put the satellite there. Therefore, you come to the kind of a backward integration to launch vehicles. So the launch vehicles enable you to put the spacecraft in orbit. The spacecraft in orbit helps you in supporting the various programs on ground. Indian space program rightly started at the application end. We didn't start with rockets first. We didn't start with the satellites first. We started with the application first. What we did is we wanted to demonstrate the efficacy of the space program for the common man. So we borrowed the so-called ATS-6 experimental satellite from NASA for 1 year in the 75-76 time frame. And then with that, we connected about 4,500 villages by community TV sets, through which both the agriculture related, health related, and education programs were beamed. So that was the first starting point of the Indian space program. So through that, we could demonstrate to the government, telling that how the space technology can enable us to cut through all kinds of communication gaps and directly reach the man in the village and then give him what he wants to know or what the government wants to convey to him. So that was the first experiment or the first space program that was done in India. Similarly, a program was done with a European satellite, French satellite to be specific, called SITE, and that experiment was done how to have a telecommunication between the mainland India and the 7 states of the Northeast. And again, it was demonstrated that how the telephony can be easily established through the space segment. Once the government could see this demonstration and then convince itself, yes, there is a great merit in this, they started funding. Then the second step, what the space program was taken was with reference to space segment. We entered into a contract with the Ford Aerospace in the US to build 4 satellites, what we call the Indian National Satellite System, INSAT-1 series. 4 of them were built and launched from US, again to build up the backbone in the space segment at the earliest. Now, once you have satellites up in the air, in the space, you can roll out all the services, whatever we talk about in terms of the communication and whatnot. So that was the second step taken in the Indian space program. Later, then we got into rocketry to have an indigenous capability, put our own satellites in orbit. In fact, it is driven more by what I would like to call the need for Indian remote sensing satellites. That's where you get to know, it must be the agricultural monitoring, it is monitoring for the floods, disaster management, every one of them is helped by the remote sensing satellites. Unfortunately, the remote sensing satellite not only senses what is in India, it also senses what is in every other country in the world. So nobody is interested in supporting you launching number of remote sensing satellites. So we necessarily need to build the launch vehicle segment. So therefore, starting with applications, going to space segment, and then we came to the launch segment. That's how the whole Indian space program has been progressed, which I think all of you will appreciate is a very rational and low, what shall I say? I will say that sustainable development mode. That's how we have gone into the space program. So of course, it started in 1962 in what is called the Indian Committee for Space Research in COSPAR, and it was part of the Physical Research Laboratory in Ahmedabad. Started in a small way, and then they selected the Tumba Equatorial Rocket Launching Station as a United Nations facility. Why it was selected was, it was in the magnetic equatorial plane. So there was a lot of interest in doing for atmospheric research in the equatorial magnetic equator, so rather put it simply. So that's how it started at near Thiruvananthapuram, called Tumba. And we started with a sounding rocket launching station dedicated to United Nations. Any country can come in with their rocket, with their payloads, launch from there and accumulate and take their data and go. So once we started making of course, the initial rockets were all brought from other countries, particularly US and USSR, then the leading countries in the rocketry. Once after seeing these rockets being launched, yes, we thought we must make our own rockets, and then that started the Indian launch vehicle program, of which I have been fortunate enough to be a part. Today we have a number of launch vehicles, as you know. I think the number of PSLV launches are becoming so numerous. I think it is no more a news item even, I think. So that is one of the most successful stories. I will come to that a little later. But then the first launch vehicle to be made is what is well known as SLV-3. The project director was none other than Dr. Kalam. So, and this launch vehicle laid the foundation for the entire spectrum of rocket technology in India. And many of them have been personally piloted by Dr. Kalam himself. Now, I presume that this conference is named after Dr. Kalam, so I would now rather like to get into what Dr. Kalam did and what are his contributions in the space technology. Of course, today we stand, as I said, we are making so many launches. We have made 3 development flights of PSLV, followed by 45 launches of PSLV carrying various kinds of satellites. We also carry a number of international satellites as a commercial service. We have also built a larger satellites called Geosynchronous Satellite Launch Vehicle 2, GSLV-2, of which I happen to be the project director. Though I have spent 16 years in the design and development of PSLV. That was my main contribution, I would always say. So 16 plus 6. So I've been in 22 years in designing and building rockets for India. So we have made about 12 launches of GSLV Mark II. Now it is now followed up with what we call GSLV Mark III, which is going to carry the Chandrayaan-2 mission on coming Monday, early morning around 2:50. So from there, of course, we have a number of satellites. The satellite also we are today, there are 17 communication satellites that are operational, all launched from India and also from French Guiana, where the satellite mass is beyond the GSLV Mark II range. There are 17 remote sensing satellites. We started off with a resolution of 1 kilometer with the Aryabhata. Today, we are below 1 meter in terms of remote sensing, and we have a whole spectrum of remote sensing capabilities in terms of the multispectral capability, which can individually pick up, which can pick up individual crops and their health. We also have radar sats, which can penetrate the cloud and then look at the ground in terms during times of monsoon and flooding and whatnot. We also have a number of Cartosat missions which can do cadastral survey of India, both elevation and plan, to a level of 1 meter. So, and the latest, of course, is the navigation satellites, what we call NAVIC. Today, India has its own navigation system with a resolution on ground better than 10 meters. And of course, India, ISRO is trying to get all these chips made and then put in various cell phones so that you don't have to depend upon GPS. You can have your NAVIC system, India's own NAVIC system for your maps and whatnot. So these are the things that as far as the growth is concerned. Of course, for the long time, we didn't have a science missions. Today, we have science missions. There are, of course, this most famous one around the Mars, okay, MOM as it is being called, and that is one of the active scientific satellites of today of India. There is also what is called Aditya, which is multispectral X-ray scanning thing, which is in orbit, looking at the space. And this satellite is unique in the sense this is the only satellite which has got from soft X-rays to very hard X-rays capability, all built into a single satellite. Whereas there are satellites which look at various bands of X-rays, but no. The Aditya is the one which can cover the entire spectrum, and it is considered a very unique and very useful satellite in that way. Of course, we are planning for more of those scientific satellites in the future also. Okay. Now, can we have the next slide? Okay, Dr. Kalam was the project director, as I said, of Pslv-3, which was the test bed on which we tried various technologies connected with rocketry. So that's why I have put the caption as a technology platform. I mean, this is we have not built any launch vehicle more sophisticated than Pslv today. We are all having much simpler ones, I would say. It has got all various technologies, and which are all now being used in subsequent generations of launch vehicles. And of course, at that point of time, we didn't know anything about rocketry, so it was totally experimental, and we need to do quite a lot of experiments, developments, and had number of failures. My own contribution in Pslv-3 was as chairman of a failure analysis board. So every failure has to be reported to me and my team, and we need to analyze and then sort out. And then it was a great learning experience because you don't know why and what failed and that kind of thing. So from that thing, we have slowly developed our technology across various fields and then mastered the whole thing today. And then we can have right from solid propulsion to cryogenic propulsion. As I have said that we, of course, modeled it one of the most successful rockets at that point of time, Scout of NASA. And then, of course, it was only in terms of looking at it, how it looks and how many stages it has got and trying to make it. But then every one of the detail is our own, we had. And, you know, at that point of time, we have made the biggest rocket grind we have made is 300 kilograms. And then Pslv-3, the first stage requires 10 tons of propellant. Now, how do we make 10 tons from 300 kilograms? So then the rocket motor was divided into 3 pieces, and we call it, and then we will assemble all the 3 pieces together, so that the requirement instead of 10 tons becomes 3 tons, or at least from 300 kg we will go to 3000 kg and not beyond. So that kind of technology was developed, and of course the avionics is totally ours. In that point of time, we had one of the most sophisticated payload fairing using fiber composite hardware, which was not in vogue, and nobody in India even would have heard of composites at that point of time. So, of course, many developments were through field, trial, error, accidents, and failures. So that's how we built up. Next, please. A number of sub-projects were made to evolve the technology. As I said, that 300 mm segmented motors, so that we can see how to join 2 independent segments and to make a full rocket motor. Okay, the control system was what we call that secondary injection thrust vector control. There was, again, it was tried out in a smaller rocket. We also demonstrated certain technologies. Okay, one of the important requirements for a rocket is you must have a destruct system if it malfunctions. So that was tried out in a smaller rocket. And in 77 or so, we made the first controlled rocket flight in India, which was made with what we call a sounding rocket, RH-560, Rohini 560, where 560 refers to the diameter of the rocket. And similarly, we did a lot of experiments in evolution of the propellants, which we can finally adopt for the propulsion. Next. So the control power plants, we had any number of them. The first stage you had two kinds of control systems, secondary injection thrust vector control. Even today it is flying in PSLV booster. We also had aerodynamic control, which we are using for the re-entry vehicles and all today. And the second stage we had bipropellant based control power plants, which is now today powering all communication satellites. What was developed in SLV is still operational, but today they are operational in satellites. The third stage had monopropellant based on hydrazine, and today that is the backbone of control for all scientific and small spacecraft. So what you see, look at SLV in 70s, they are all systems that are operational even today in other rockets. Of course, Dr. Kalam personally took very initiatives in certain technologies, and all of them became later directorates in Vikram Sarabhai Space Center. There was pyrotechnic devices and systems. You need a lot of pyrotechnic systems in the rocketry to separate, to destroy, and all that. So they were all developed, and then it became a directorate by itself. And we have what is called aerospace mechanisms. You have to have so many mechanisms to deploy the rocket, payloads, deploy antenna and whatnot. So that again was started by Dr. Kalam. And most importantly, he started the composites. It is way back in the 70s. And then he started a separate center for it, what is called reinforced plastic centers, in short form REPLACE. That was also started by Dr. Kalam. So in all four, we had 4 flights of SLV. The first flight was a failure, in which was explained by Professor Satish Dhawan, then the chairman of the Indian Space Research Organization, as partially unsuccessful. And people are trying to decode it even today. What he meant by that? Okay. So the second one was successful. The second one was very successful. So that was when we said that, look, we are in the space club. And of course, we made 2 more launches. After Dr. Kalam left the SLV-3 after the second launch in 1980, he moved on to headquarters, and he was there till 1984. Then he moved on to DRDO. So of course, then we went on to the other launch vehicles. The PSLV was one of the first operational launch vehicle developed, and it was a quantum jump in size. The SLV-3 was 1 meter in diameters. Now PSLV, all dimensions are 3 meters and long, and then it is in 42 meters tall and weighing something like 312 tons on the launch pad. So whereas SLV was 1 meter diameter, 21 meters tall, and then weighing 17 tons on the launch pad. You can just look at the kind of magnitude of the jump is sort of made at that point of time. And technology-wise, it's way beyond SLV-3 also. We were introduced first time liquid propulsions in the launch vehicle. The second stage and fourth stage were liquid rockets. And we had all digital electronics with onboard processors and whatnot. The type of construction was very different. And first time we had to work on superalloys like maraging steel, which is 4 times as strong as steel. We had a titanium alloy tank for the 4th stage and high pressure gas bottles. And we had to also have aluminum alloy tanks and all that. So we need to have an entire set of new technologies to be developed. And in India at that point of time, when you say you want to do a rocket, it's not that you make a design and pass it on to industry. Every single thing has to be developed. If you take the maraging steel, the development of the steel, converting into products, developing the welding technology, everything was done by ISRO. So the space program, when we talk, it starts with the metal making, not necessarily design and fabrication. No, you have to start making the metal. That's how the whole thing has been. Okay, so we went through all that phase and that. So the staging and other events were all based on onboard decision logic, so that it became autonomous and it can cater for the variations in the performance of the stages. First time we need to have a guided injection into the spacecraft. Spacecraft in SLV-3 was an open loop kind of thing. It performs and puts into some orbit with a large dispersion. But here we are talking application satellites like remote sensing satellites. We need to put it, if it is going to be 820 kilometer altitude, it has to be within plus minus 5 kilometers. So it went for a lot of controlled injection and all that. Of course, we had a large payload fairing which was covering the satellite, which is 3.2 meter diameter and 8.5 meter long. It's a huge one. Okay, next. So we had 3 developmental flights of PSLV, of which I was part and parcel. We had that first failure again 1993, which was a failure. The failure occurred because of software overflow in the computer. And they were corrected. Since then, it has been totally successful. And one of the workhorse rockets of ISRO or India is PSLV. Incidentally, there is a contribution of Dr. Kalam in PSLV also. If you really look at it, PSLV, it is a core vehicle with 6 strap-ons. Originally, the project was pushing for a huge modular strap-ons. That is, there is a 125-ton propellant loaded central core stage and 2 strap-ons, 2 additional motors added of equal size. That means 125 plus 125-ton propellant. Dr. Kalam said, no, you don't go for it. Please take the SLV first stage as strap-ons and then use it. So he was very insistent. Then finally, that was how the configuration was decided. What it has enabled in PSLV to do is, we have 3 configurations of PSLV today flying. If PSLV without a strap-on, PSLV with 2 strap-ons, PSLV with 4 strap-ons, PSLV with 6 strap-ons, depending upon what is the payload requirements. So that kind of flexibility came out of Dr. Kalam's idea. Of course, once we had that capability for launching the remote sensing satellites, we needed to have the capability to put the communication satellites into orbit, which means 36,000 kilometer altitude as compared to low Earth orbit of something on like 800 kilometer orbit. So we went into the development of GSLV, which of course drew, as far as the first and second stage is concerned, all the technology from the PSLV, but then the third stage has to be necessarily cryogenic. So that was a new development for the GSLV. Of course, the first, initially we had a Russian contract for the development and supply of a cryogenic stage to India. So that's what we had. Subsequently, we developed our own, and currently it is flying with our own cryogenic stage. Next. I think I will skip it maybe 2 minutes. Next. I know how visible it is. The rocket, once it leaves the ground, it is totally autonomous. There is no pilot sitting there to take care of any kind of contingency. So everything has to be built into that, and everything has to work to the precision. If any single thing is missed for even a second, you are going to lose the launch vehicle. That's where the challenge of launch vehicles do come in. And okay, we have a first stage which operates for something like 160 seconds and gives a velocity of something like 2.5 kilometer per second within that 160 seconds. The second stage then takes off, and then it burns for another 160 seconds, and then pushing the velocity from 2.5 kilometer per second to 5 kilometer per second. And then the cryogenic stage takes it from 5 kilometer per second to something like 11 kilometer per second ideal velocity. That's the kind of thing that is required. And India has got certain geographical limitations, because the first stage and second stage after use is going to be dropped into the sea or onto the ground. And then we can't drop it anywhere. We need our own sea where we can put it. So if you really look at it, to put a communication satellite, you have to launch due east. If you really look at east of India geographically, that's, once you cross Andaman, you have Thailand, you have Indonesia, Philippines, and whatnot. So a whole lot of things. So all our rockets have to be so designed that the second stage falls in the Andaman Sea, and then the third stage gets into the orbit. So it is a one constraint imposed by the geographical location of India within which we operate. Okay, this is the liftoff sequence, normally there is about T minus 12 minutes, the computer takes over the thing. Then on, it is all totally on the computer-based operations, where the people sitting there in the control center can only watch what is happening. About T minus 4 seconds, T0 minus 4.6 seconds, the liquid strap-ons ignite in the case of GSLV. And then if their health is checked, if the health is okay, all the 4 stages or engines are operating normally, then the core solid motor is ignited at T0, then the vehicle lifts off. And then once it clears about rises about 90 meters, then it starts pitching in and then follows the program, pre-planned program to put it in the particular trajectory. Next. Yeah, after making the JSLV-3, we need, of course, the satellite mass has been going up at one point of time, and also we need heavier launch vehicles for with a view of having a manned programs and things like that. So the GSLV Mark III has been conceived on that for that purpose, and already we had 2 flights. The 3rd flight is the one which will be taking the Chandrayaan-2 mission on coming Monday. So all of you heard about Chandrayaan-1 program, and here Dr. Kalam had a very specific contribution to make. And what I put on the top, Moon Impact Probe, it was not there as part of the original Chandrayaan-1. But then when this project was, when the details were presented to Dr. Kalam, he was then the president, of course. He said, he insisted, and I must say, look, what's the point you guys going and turning around the, okay, top, yeah. What's the point you guys going to the moon and going around the moon? You must put our flag on the soil of moon. So then this small spacecraft, small part here, what we call the Moon Impact Probe, was engineered. And the purpose is, after it gets into the orbit, it will separate from the main spacecraft and go and impact on the moon, and carrying an Indian flag, so that the Indian flag is put on the soil of moon. Okay, so it was agreed a special rocket motor of small size was developed to retard the probe, and then so that it can land on the moon. Oh, I missed that view graph. This one. Okay, that's not it. Sorry, I think it is there on the. Okay. So therefore, it was specially made at the request of Kalam, and then it was accomplished also. Okay, as it is now, this is the what we will be having on Monday when we launch the Chandrayaan-2. The mission-wise, it is no different from Chandrayaan-1. First of all, the Mark III rocket will put it in a lower elliptical orbit, and then the orbit will be successively raised. And then there will be a what called translunar injection, when the orbit will go all the way, apogee will intersect the lunar path, and the moon by its gravity will capture the spacecraft, and then afterwards it will be on the lunar circuit. And then it will be orbiting around the moon for almost 27 days before it goes and lands on the moon. Next. No problem? Okay, so I'm sure all of you are following the Chandrayaan-2 program in the newspapers, and it has got 3 elements. The first is, of course, there is an orbiter which is going to orbit around the moon. There is going to be a lander. The lander has been appropriately named as Vikram, and then that is the lander which will go and land on the lunar surface. And it has got a rover named as Pragyan, which can roam around the moon and for the experiments. So the most crucial phase of the entire program is, yes, we can get into the lunar orbit and all, and going and landing on moon is going to be very tricky. So this is a kind of thing that gives you how the Vikram is going to maneuver and then go and land on a designated spot on the moon. Okay, moon is not a very smooth surface. There is supposed to be too many craters and too many boulders. The whole thing is the safe landing is a big question. And what we have on board to sense whether the area is clear or not is only a camera. And then the logic from the camera must pick up at the correct position, maneuver the spacecraft to that point, and then go and drop there exactly. So I will say that that is one thing that, yes, everybody, we are, to the best of our imagination, everything has been done. Okay, but still we must keep our fingers crossed whether we really achieve it. And hopefully we do it, and we will be as usual. Every single mission we have taken today, either Chandrayaan or Mars mission, our first mission has always been successful. And we do hope we have done enough homework to make this mission also successful. I think that's the end of that, right? Oh, yeah. All right, this is the one view of that. You can see this. The spacecraft, when it is assembled, it is something like 6 meters tall. That means a 2-story building is what the height of the spacecraft is. And you can see the payload shroud, which is 5 meters in diameter and 10 meters in length, which is a huge one, which is made to accommodate, house the spacecraft. And right today, the checks are going on the launch pad, and everything looks go for the launch on Monday. Okay, with this I complete my presentation. Thank you. I do hope I conveyed both what Dr. Kalam has given to the space program and also to what Indian spacecraft is all about. Thank you. Any questions? I hope. No. No.
It's too early for that.
Yeah, it's too early. And also, look, I mean, if you want to bring it back, you must have enough propellant to be carried all the way there, right? To bring it back also. So that will call for, I mean, Saturn V's launch vehicle is enormous. It's 100 meters tall, weighing something like, I mean, in excess, I don't remember the value, maybe close to 1,000 tons or plus. And bulk of it, I mean, cryogenic propulsion, which gave that efficiency for it. It's a phenomenal thing if you want to bring it back, anything from space. Because you see the rocket on the ground, right? As I said that this Mark 3 rocket weighs 610 tons at liftoff. And then it is capable of putting 3.8 tons in the lunar orbit. Let's say we want to bring some 1 ton from there. You know, the kind of, again, the energy required, the propellant required, that means you have to carry a rocket also along with the spacecraft to moon. So that we can fire it back towards Earth and land here. We are not into that yet. Yeah, please.
Yeah, thank you for the fascinating talk and the excellent history. When you were mentioning the Chandrayaan-1, there was a lot of NASA collaboration as well. I mean, even from the first early days with Pslv-3. With the last 2 months ago, their announcement with the Artemis program, which is NASA's program to go back to the moon. Do you guys feel like there's going to be forged relationships in moving forward?
No, I'm not sure about Artemis. Okay. No, dealing with Americans is very difficult. In the first place. Okay. In Chandrayaan-1, we have carried NASA payloads. Yeah. Particularly the payload which is supposed to have detected the presence of water on the lunar subsoil is a NASA payload carried by an Indian spacecraft, and then data handling done by India. But then to do that, we have stood our ground, telling that we do what we do. If you agree, sign the contract. Otherwise, you don't have to sign the contract with us. Because the kind of conditions they put is, they will not allow even us to go and see our spacecraft. That was the kind of things they were insisting on. Okay, so okay, finally NASA signed on the dotted lines of India. Thank you. We would be fair, but then we are not game for an, imperialistic kind of clauses being stipulated on us.
Sir, you were speaking about the payload capacity, which was said to be around 4 to 5 ton to LEO or GTO. But comparing to other countries like US, Russia, China, even Japan, they have varying capacity from 14 to 27 ton, while India just have 1/5 or 1/6 of the capacity. So is ISRO looking at increasing the capacity in that sense?
Yeah, we will be increasing the capacity. First of all, see what you are talking about is the low Earth orbit. Low Earth orbit, our capacity will be larger. Okay, the Mark III, what is putting is it's like a geo transfer orbit, where the payload capacity is 3.8 tons. If you talk about it on the
GTO.
low Earth orbit, it's almost more than double kind of thing. Number two is, as I said, we have a unique constraint because of the geographic location. I can't have the first stage, big first stage, because I have to still be within the Bay of Bengal. Whatever I drop, I must drop in Bay of Bengal. And whatever I don't drop, I must take it into orbit. It's very...
And the second question is related to the first question. We have actually acquired a relaunch vehicle capability technology, right?
Okay, we have been doing a lot of technology demonstrator programs like hypersonic combustion and hypersonic re-entry vehicle and all that. Probably we are not putting in, though we have been successful in both efforts, we are not putting great emphasis or putting record resources into them, because we are operating within the resources available for us, which is more towards application oriented. Yeah, you want to say?
Was US help crucial for the success of Mars program or not?
No, let me put it this way. We have a good relation with the JPL. Okay? For example, if we want to get a gravity model of moon, okay, they have like a good gravity model. So we try to borrow from them the gravity model so that our orbit, what we do, is more realistic, right? So with reference to this kind of information exchange, yes, the answer is yes. Now, a second type of help we need is, we need ground station all around the earth. We don't have it. We have, our ground stations are in India, the Andamans, the Indonesia, and also Brunei. Okay? These are the 4 ground stations we have. We have one now in Antarctica also. But then this kind of missions call for Australia, American mainland itself and all that. So for those ground stations, we are dependent upon definitely JPL. So and the JPL also helps us. They come and review whether what we have all done is sufficient, whether they feel that we must do from their experience something additional. That kind of exchange also is there. Yes, they are good, they are welcome, they are essential in a way.
Sir, so basically the issues which you will be facing after the launch, is it going to be similar to the Mangalyaan mission, or are you seeing something particular that which might be a problem during the launch and during the landing, other than the crater this thing?
No, as far as the launch is concerned, there should be nothing more crucial than what we already, Chandrayaan 1 we have Mangalyaan 1, Mangalyaan. So no, launch-wise we are absolutely clear. We can go get into the lunar orbit, no problem. The landing phase is new. There can be gravitational anomaly, and also you see, you take assumed shape of moon, but then local terrain is not the assumed shape. Okay, local terrain may have 100 meters tall. I mean, outside the envelope or 100 meters below the envelope. So these are the variables. Okay. What is planned is, okay, we are going to be around a lunar orbit for almost 27 days. So actually launch is this Monday, but then landing on moon is only September 6th. There are 27 days of orbiting around the moon. So we hope to collect a lot more data on the landing site and things like that, and get a better picture and all that. And also we have data like Chandrayaan 1, we had a stereo camera which has put, stereoscopic pictures are available. Using all that, but still, and also you must note that the propellant what we carry will be just enough to go on land, make one attempt, nothing more. So every system must work paka. No compromise on performance, no deviations, no failures. That's the kind of scenario. Yeah. So, I mean, obviously, probability is against failure is never zero. There is a definite probability.
Sir, and one more is, what's the best kind of result you will be expecting once you land on moon? Like, what would be the thing which you would be like, yeah, that is the success of our mission?
What I would
Like, what kind of a result which you would?
No. Okay, basically we would have made a landing. Okay, that is something really good. Number two is we are carrying about 16 scientific payloads. The whole purpose is it's a science mission. So we are having a lot of science things to be accomplished by going to the moon. So we want all the 16 experiments to be successful. Okay.
Thank you, sir.